Hello, everyone. My name is Lili Chan. I am currently Associate Professor in the Division of Nephrology at the Icahn School of Medicine at Mount Sinai. Today, I'm going to talk with you about artificial intelligence in kidney care. These are my disclosures, and they're unrelated to the talk I'm giving today. The learning objectives of the talk is to go over what artificial intelligence is, how to assess model performance, how has AI been used in nephrology, and we're going to end with what are barriers to implementation of AI into nephrology clinical care. So what is artificial intelligence? It is the overarching technique that enables a computer to mimic human behavior. Machine learning, which we often hear more about, is a subset of artificial intelligence, where you take massive amounts of data and find patterns which are used to classify the data or to generate predictions from the data. There's also deep learning, which is another subset of machine learning, which uses artificial neural networks to learn patterns. We'll mostly be talking about machine learning during this talk, since this is what is most commonly used in nephrology. So AI really is everywhere. Here is an example of using Google Maps, which uses data from users to estimate the travel time between point A and point B. Another example is Amazon, which uses your data from your past purchases and your browsing history to suggest other items for us to buy. And lastly, Google Translate, which uses artificial intelligence and natural language processing to translate from one language to another, here English to Spanish. So how does this really work? Well, first you start with training data, and this is data you are going to give to the machine learning model to learn. And this is going to result in a machine learning model, which then you apply to test data. Testing data should always be data that is reserved from your training data and not previously exposed to your model. You will then get either a prediction or classification depending on the task you're trying to do. Then you want to evaluate the model to assess the performance of your model. If the model isn't working as you want it to, then you have to go back and retrain the model either with new data or changing the hyperparameters of the algorithm to generate a better model. So machine learning can generally be classified into two buckets. There's supervised learning and unsupervised learning. In supervised learning, data is labeled to tell the machine what to look for. This is often used for classification. So for example, you'll have pictures of cats and dogs, and you're training the model on pictures of cats and dogs, and then you'll give it a new set of pictures and ask the model to classify these pictures into cats and dogs. So here in the bottom are the different types of algorithms that can potentially be used for classification purposes. Supervised learning can also be used for regression. So this is using to predict a continuous outcome. One example would be that you give the model or the algorithm the age and gender of a set of people, and then you ask it to now predict the height of these people based off of training data. And here again on the bottom are different types of algorithms that are commonly used for regression purposes. And what you can notice is that while some of the algorithms can be used for both regression and classification, such as neural networks, there are some that are unique to classification and regression. Now going to unsupervised learning. Here you're giving the machine data that has no labels. You're asking the machine find whatever pattern it can. And this is often used to do clustering. So an example of this is marketing, where you're asking the model to identify a group of people who would potentially be interested in purchasing some product and then sending their advertisements that way. Again, here on the bottom are different types of algorithms that can be used for clustering. There is a third type of machine learning called reinforcement learning, which learns by trial and error to achieve an objective. So one example of this is Google's AlphaGo, which was a program that was developed and actually beat the top human Go players in the world, was in the news a few years ago. We're not going to talk too much about reinforcement learning, mainly because it hasn't been used too much yet in nephrology research. We briefly talked about deep learning. So again, deep learning is a subset of machine learning where you're using neural networks modeled after the human brain. Here on the right, you have an example of a simple neural network made up of one input layer, one hidden layer, and one output layer. At each layer, there are nodes which connect to another node with associated weights and thresholds. So if the output of any of the individual nodes is above the pre-specified threshold, then that node is activated and the data is sent from the inner layer to the hidden layer. If it's not, then the data is not sent forward. This is called a feed-forward network. Traditional machine learning is different from deep learning because deep learning generally requires less human intervention for the results. However, it does require more computational resources, more time to set up, and needs a lot more training data. So how should we be assessing these models that we're seeing in the literature? If we're talking about regression models, one common metric is the mean squared error. So the average of the squared difference between the actual value and the predicted value. Here on the figure here, there's the creatinine on the y-axis and age on the x-axis, where each x indicates the actual creatinine value for that age, and the blue line here indicates the predicted values. And so what you're actually doing here is you're taking the difference between the actual value and your predicted value and then squaring it. And because you're squaring it, you actually have and can overestimate how bad the model is because you're penalizing these small errors. However, it is very good for identifying outliers because of this penalization. Another common metric you'll see is the mean absolute error, which is the average of the absolute difference between the ground truth and the predicted values. Again, X here indicates the actual value, while the blue line here indicates the predicted value. And you're taking the absolute difference from the actual to the predicted. And this can give you a measure of how far predictions are from the actual values. However, because you're taking the absolute value of these numbers, you're not going to have an idea of whether the model is over or under predicting the actual data. Moving on to classification models, here you have a confusion matrix, which is made up of differences between the ground truth and the predicted truth. And this is just a simple 2x2 table. And using this 2x2 table, you can identify metrics such as accuracy, how close is the model prediction to the true value, recall, or what we commonly call as sensitivity or the true positive rate, what proportion of actual positives are identified correctly. And lastly, precision, or also known as positive predictive value, what proportion of positives identified by the model were actually correct. F1 score is a combination of the precision and recall, and also commonly reported in literature. And it's useful because you may want to oftentimes balance precision and recall. So if you have a high F1 score, that means that both your precision and your recall is high. However, if your F1 score is low, this is not as useful because you don't know whether it's the precision or the recall that is low. This is also another familiar metric. This is the area under the receiver operating characteristics curve. And the ROC tells us how good the model can distinguish between two things, where a higher value is better. A value of 0.5 indicates that's a chance. So if a model has a 0.5 or close to 0.5, it means that your model is not performing any better than chance. Something that you may not be as familiar with is area under the precision recall curve, where your precision is on your y-axis and your recall is on your x-axis. And the ROC curve may not be representative of the data if the data is imbalanced, meaning that you have very few patients who have the actual event. So the PRC curve, the PRC is better because it actually focuses on the positive class and not so much on the true negative. And so you would want to use this if your data is imbalanced. So how do you know what chance that your model is performing better than chance? So chance here is actually the proportion of positive cases. So in this case, chance was 22% of patients had the event. If your PRC is a bit higher than that, that means your model is performing better than chance. So what has already been done using ML in nephrology research? Prediction of AKI has been really extensively looked at. And so we know that AKI is common in patients hospitalized and is associated with increased morbidity and mortality, and that identifying patients who are at risk for developing AKI may allow for institutions of mitigating factors. And so this, like I said, has been a topic of a lot of people's modeling. And here is a summary table presented back in 2020, looking at several different models developed in 2019 at various different settings and with various different performances. And we're going to talk a little bit more about the Tomasev et al. One. So what the researchers did here is they used data from the Veterans Affairs from 2011 to 2015. They de-identified the data and then sent this over to Google DeepMind. Data features included ICD codes, CPT codes, lab results, medications, and vitals. Here in the figure is actually how they used this data and used it for the model. First, they separated the data into outpatient events and admission events. And then because things such as vitals or laboratory results can be repeated during a day, these values were binned by when they were obtained into 4 potential time buckets, so every 6 hours. If the value did not have a time or an unknown time, it was binned into this kind of 5th time category. features from 48 hours prior to when your model is triggering was then used to train the model, and the model was asked to predict whether or not the patient would have AKI in the future of 24, 48, 72, and other timeframes. All of this data was split into training, validation, calibrating, and testing set, and they defined AKI using the KDIGO creatinine criteria. This is the model architecture that was provided to us, and we're going to start here at the bottom. So like I said on the previous slide, this data is very high dimensional and sparse because there's multiple repeats. People could repeat at different time frames. And so what they use is deep embedding, which changes high dimensional inputs into a lower dimensional representation. This data was then fed into several RNN cores. RNNs are recurrent neural networks. It's actually a deep learning model. And this was then used to output a prediction on whether or not the patient would have AKI across 8 different time points. And they had a secondary aim of predicting the maximum of future observed values for a set of labs. Here's an example of the results that they, example patient. So here on the top, you have the actual creatinine values of a person who is admitted from hospital day 0 to hospital day 8. And here you can see that around hospital day 5 is when the patient met AKI criteria by creatinine. Down here is the model prediction of AKI. So in the green line, along with the 95% confidence intervals, are the actual probabilities of whether or not the patient would have AKI at 48 hours. This red line here is the threshold that they use to identify, to say that if the prediction is above this value, then the person would have AKI in the next 48 hours. And here at hospital day 3 is when the model met that threshold. And at hospital day 5 is actually when the person developed AKI. So this was an accurate and correct prediction. At each of these model prediction time points, it also predicted the laboratory results of the serum creatinine, the serum urea nitrogen, and the serum potassium values, again indicated here by the green lines with the actual values here in the blue lines. So overall, the trends for the laboratory results were also pretty consistent. Here is the ROC, AUROC, and the AUPRC curves for the patients. And you can see again, your AURC is greater than 50%, which is indicating that this is performing much better than chance. And your AUPRC was 29.7%. And the proportion of patients who had AKI was 14% in the study. So again, this suggests that the model is performing better than chance. The model also identified 55.8% of inpatient AKI events up to 48 hours in advance. And for every 2 positive predictions, there were 2 false positive predictions for every true positive prediction. So summary number 1, deep learning using longitudinal data can be used to predict AKI up to 48 hours before onset of AKI. Major limitations of the study is while they had 172 medical centers, all of them were part of the VA and therefore used the same EHR system. Another important factor to note is that 94% of these patients were male gender, and it's unclear whether or not this model developed in male gender would apply to people of other genders. Now we're going to move on to risk prediction of progression of diabetic kidney disease. So we know that patients with DKD can have several trajectories of their kidney progression. Some patients will never progress. Some patients will rapidly progress. And there's all these other patients in between. The currently most used kidney failure risk equation or prediction model is the kidney failure risk equation, which was developed by Tangri et al. And uses these 8 different clinical features. However, it's important to note that only 37 and 38% of these patients had diabetes. Also, the baseline eGFR of patients in this study was 45. So these were patients who had relatively late-stage diabetic kidney disease, and it's not clear whether it would apply to patients who were earlier on or had early diabetic kidney disease. So Kidney IntelX is a model where we aim to combine biomarker data with EHR data to generate risk predictions for patients with diabetic kidney disease. In the study, we used data from the Mount Sinai Biobank, the UPenn Biobank, and we specifically looked for people who were in the moderate risk of developing or having progression. Baseline eGFR were values between 1 year before and up to 3 years after biobank enrollment. We had follow-up of at least 21 months, and they had to have equal to or more than 3 eGFR values after baseline. we split the data into derivation and validation sets, and the derivation set was further split into training and testing. The primary outcome in the study was progressive decline in kidney function, which was defined as rapid kidney function decline, sustained decrease in eGFR, or kidney failure. These were the different features that were eligible for inclusion into the model, which included demographic information, laboratory values, including 3 plasma biomarkers, ICD-9 and 10 codes, medications, and vital signs. The model that was used, the algorithm that was used to develop this model was random forest. So random forest is a decision tree-based algorithm. So how does a decision tree work? Here is an example of potential data that you want to classify. So one potential node might be, is it red? Which will then split it already into these, no, the blue zeros, and then the ones and zeros here. And then you could further have, is it underlined? And again, now you have classified all of these different values into groups. So what's different about random forest from a simple tree is that it actually uses multiple different trees that you pre-specify how many trees and what length of the tree. And each tree will then subsample the test data and generate a prediction based off of that tree. And so it then gets condensed down and combined either by averaging all the predictions or using a majority rule to generate one overall prediction. And this makes a result that is much more powerful than a simple decision tree. So here are the results of that random forest model. In the kidney intellects, the derivation and the validation both had an AUC of 0.77, and this was higher than a comprehensive clinical model, which was developed by Nelson and published in JAMA 2019, and which had an AUC of 0.61 and 0.62 and 0.61. Here on the right is actually a SHAP plot, which gives us some information about feature importance. So features that were more important or influential in the model are higher up. And how you interpret this is if we look at the serum calcium level, you can see that a purple dot here would mean that they have high calcium levels and would push the model to predict that the patient would not have the outcome of interest, while a yellow dot, which means that the patient at low calcium values, would push the model to suggest that the patient would develop the outcome of interest. Here are the patients actually sorted by the predicted risk. So the higher risk individuals here on the right, as you can see, there are more orange dots indicating that patients who did have higher predicted risk did have true progression, while those who had lower predicted risk did not have progression indicated by the blue dots. And this is the same in the derivation and also the validation set. We then further classified patients based off of their kidney NTLX scores into 3 categories: low risk, intermediate risk, and also high risk. We looked at survival here as Kaplan-Meier curve, and the outcome here is a sustained 40% decline in eGFR or kidney failure. And you can see that survival was much lower in patients who were identified as high risk by kidney NTLX. Here on the right are the actual hazard ratios. And so patients who were high risk by kidney NTLX were 9 times as likely to have the outcome compared to the intermediate and low group, and 15 times compared to just the low group. So in summary, a random forest machine learning model uses biomarker and EHR data, can identify patients at higher risk of a composite clinical outcome. The random forest model had better performance than a clinical model, and plasma biomarkers were top features in the model. The major limitations to this study was that we had high missingness of the UACR in the cohort. Around 30 to 40% of patients did not have a UACR value. However, this is similar to true clinical practice, where oftentimes patients don't have a UACR measured. We did not identify patients who had a biopsy-proven diabetic kidney disease, and therefore we may have included people who have other forms of kidney disease. Our last study that I'm going to talk about today is using ECG to determine left ventricular ejection fraction in patients who are in hemodialysis. So in this figure, showing the cumulative probability of developing heart failure in patients with chronic kidney disease and various forms of renal replacement therapy. Patients on hemodialysis, indicated here by this gold line, had the highest cumulative incidence of all other participants. So not only is heart failure extremely common, it's also associated with mortality. Here you can see that patients who had heart failure with reduced EF had the lowest survival compared to patients with no heart failure. Patients with heart failure with preserved EF and patients with moderately reduced EF. So while echocardiograms are actually the definitive way of evaluating left ventricular ejection fraction, ECGs do offer a snapshot view of patients' cardiac function. They're cheap, frequently done, and can be obtained in an outpatient setting. And therefore, we attempted to build a model to predict LVEF using ECGs in patients on hemodialysis. Since machine learning models, though, require a large amount of training data, building a model using just data from hemodialysis patients may not result in a high-performing model. So what we utilized was transfer learning in the study. So in transfer learning, you train a model using larger generic data sets for a generic task. You then take the model developed in this generic task, and then you apply it to your specific data set, and then you further do fine-tuning on your model to predict your specific task or perform your specific task of interest. And this should result in a better model using much less data. So in our study, we used ECG and echo pairs from 2,000 HD patients and approximately 150,000 non-hemodialysis patients. And we had trained our models using 4 different strategies. Trained from scratch, which is we trained on HD patients and then we tested on HD patients. Pre-trained on ImageNet, so we trained on these ImageNet data, which is an online large visual database. And then we fine-tuned on hemodialysis patients, and then we tested it on hemodialysis patients. A model that was trained in non-HD patients and then tested in HD patients. And finally, a model that we trained on non-HD patients, did fine-tuning on HD patients, and then tested on HD patients. So this is the overall performance of the 4 different strategies for the 3 different categories of LVEF. And what you can see and what I want to highlight is that the model that is transfer learned, meaning trained in non-HD patients and further fine-tuned in HD patients, have the highest AUC for all of the 3 different LVEF categories. Here on the right are the AUU ROC, the ROC and the PRC curve for the model that it was the transfer learning model. And lastly, this is the survival probability of patients, specifically for death in patients who had LVEF of less than 40% predicted by our model. And you can see that those who were true positive and also false positive, those who the model predicted had an LVEF less than or equal to 40%, had much lower survival compared to the negative. So in summary, an ML model using ECGs that was pre-trained in non-HD patients and further fine-tuned in HD patients is superior to models trained from scratch and only in HD patients for identifying ejection fraction. Major limitations is we actually did use data from 4 different hospitals. However, it's still a single center study as they were all Mount Sinai Health System hospitals. Lastly, we use inpatient ECG data, which might not be representative of a steady state outpatient hemodialysis patient. So we're going to end our talk today with a discussion on potential different barriers to AI integration into clinical care. So one of the most common issues with our published models is that they lack external validation. Here on the right is actually a table of several AKI prediction models, and unfortunately, none of them had any external validation. This is an important point because without external validation, we cannot know if the model will generalize to other patient populations. We know that models perform better in data that is from the same cohort or similar to the original cohort than new data. This may be because models are overfit to the data, meaning that the model has memorized details from the training data and will therefore not generalize to new data. There may also be biases in the model, such as site bias and selection bias, which is related to differences in treatments and demographics of the original patient population. And external validation is difficult to achieve because it's difficult to share granular data. And NIH has new data sharing policies which are getting implemented, which will require research studies funded by the NIH to submit their data to the NIH for public use. There's also new machine learning techniques such as federated learning, which doesn't require sites to send granular data and are also starting to get tested in nephrology research. Another barrier is that EHR data is extremely messy and often unique to each healthcare system. And so putting it all together requires a lot of data cleaning. New data models such as OMOP are increasingly adopted by health systems, which will hopefully standardize EHR and make it easier for institutions to collaborate. It's also important that models we develop are actually going to be used. And part of that challenge is that ML models, particularly those that are deep learning models, have limited interpretability. So it's often called the black box because you put data in, the model runs, and then it generates a prediction. But what's happening and what features are contributing to the model prediction is unclear. So we need to have better ways of identifying which features are important to the model. And SHAP plots are one of the newer things which I discussed earlier that's helping to identify feature importance. Models also have to add to the care of patients and not impede workflow. We already get so many alerts in the EMR that we are at risk for alert fatigue. And lastly, we want to make sure that our models are providing a prediction for an outcome that is going to be actionable. So if a model gives us a prediction that a patient is going to develop some outcome too late in the disease course, then we're not going to have time to actually intervene and change the course of the disease. And when we're actually evaluating models, we have to evaluate whether or not the model has bias in it. Because if we give the model biased data, if we train the model on data that's already biased, then the model will inherently be biased. So one example that was in the news recently was Amazon's hiring algorithm, where they trained a machine learning model to identify applicants who should be hired for technology jobs. Since technology is such a male-dominated field, the training data was predominantly male, and the model trained on this data ended up penalizing applications that included terms associated with women. So how can we potentially prevent bias? We need to ensure that our models are developed and tested in a diverse population. We have to ensure that data collection is occurring systematically. We're not selectively asking certain questions to some groups and ignoring other groups. And there are ways of measuring bias in models, and one commonly used method that's cited is the PROBAS method. So in conclusion, machine learning is already being used all around us in our daily lives, and there is a growing body of research using machine learning in nephrology. And there are several barriers that are currently existing, and multiple people are trying to address this. Multiple governing bodies are trying to help break these down so that we can increase the use of machine learning in nephrology and also implement it into clinical care. So with that, I'm going to just thank my mentors and also all of the members of our lab pictured over here. And if you have any questions, feel free to email me or find me on Twitter. Thank you. Bye-bye.